Welcome back, Mindsetters. Remember that we are doing grade 12 mathematics and we're going through some past papers. This is a revision session, so make sure that your questions are relevant to the revision that we're doing right now, just so that you are getting so much more from this one section, guys. This is very important. Easy marks, but very important marks. So just make sure that you are focused, guys, because in this section, you can get literally every single mark and literally pass with flying colors. So make sure that you are 100% focused and ask anything that you need to ask on what Natasha is doing. If you do have the paper next to you, then maybe it's a good idea to look through it as well. Check what's there that's bothering you, and then you can actually send us the question. Over to you, Natasha.
Okay, thank you, Katlego. All right, guys, so remember we are doing a calculus question from the November 2010 paper. So in this section, what I would like is if you have questions on calculus, please send those through. In the next half, we will look at paper 3, which will be geometry questions. But for now, if you have calculus or any kind of algebraic question that, you know, kind of gets you a lot of marks, because I know a lot of the times people start asking word problems. Now, I know that, you know, when you're in the exam and, you know, you see this word problem, it can really, really bug you down. But guys, it's not as much marks as calculus. So I prefer to concentrate on sections that are really going to give you guys a boost in the exam and give you some good revision to write paper 1. Okay, so for now, we're looking at calculus. All right, so we are on to part 9.4. Okay, we've just worked out that the coordinates of the turning point of the original graph G was going to be at x is equal to -2 and x is equal to 6. The next one is to now write down the x coordinate of the point of inflection. Now remember, the point of inflection is the point at which your second derivative is equal to 0. Okay, so point of inflection is where your second derivative is equal to 0. So how do we find points of inflections? Yes, we take the second derivative, equate it to 0, and then solve for x. Remember, we have the graph of the derivative already. We already know what the equation g dash x is equal to. We've got a third x squared minus 4 third x minus 4. So if I wanted to find the points of inflection of the original graph, I could derive this, because remember, this is the first derivative. So if I wanted to find the second derivative, I could just derive this equation here. But let's go to the graph and let's explain to you what's happening. Okay, remember, point of inflection is where your second derivative is equal to 0. Okay, so if we interpret that in terms of the graph that we've got, because remember, this is your graph of the derivative. So if I were to derive this graph again, right, that would be your second derivative. But remember, your point of inflection is where the second derivative is equal to 0. And on this parabola, where is the second derivative equal to 0? At the turning point. So therefore, when they're asking me for the points of inflection, they basically want to know the x value at point B, because that is where my second derivative will be 0. It will be at the turning point. Okay, so if I know the coordinates of B, then I will know what the point of inflection is. Okay, well, if I know the x value at the point B, I will know what the x coordinate of the point of inflection of the original graph is. Okay, all right. So how do I find point B? Well, it's at the turning point of the parabola, which means it's exactly midway between C and D. So therefore, to find the coordinates of point B, and this is number 4, to find the x value, all I say is it's the turning point of the parabola. So how can I find it? I'm going to say x is equal to exactly midway between the x-intercept, so -2 plus 6 divided by 2. So that's going to be 6 minus 2 is 4 divided by 2 is 2. So therefore, the point of inflection of the original graph will be at the point x is equal to 2. So There is another way you could do it. This is the way we did it, showing the midpoints, because obviously the turning point of your parabola is exactly midway between the x-intercepts. So I added them and then found the midpoints of those two. The other way you could do it was to take your equation for your parabola, a third x squared minus 4 over 3x minus 4, and use the formula for your axis of symmetry. X is equal to minus b over 2a. You could have done it that way. Or if you preferred, you could have even taken this equation and derived it and then made it equal to 0 and solve for x. Either way, you will get the same answer. Okay. All right, guys, the last part of this calculus question. Explain why g, now g, they're talking about the original graph. Explain why g has a local maximum at x is equal to minus 2. So, let's look at our derivative graph. Remember, at this point, x is equal to minus 2. It's where your original function is turning. It's the turning point of your original function, okay? And this derivative is 0 at that point, okay? So, if we want to explain why it is a local maximum, now remember I've already shown you that because we're dealing with the positive gradient, this is the kind of shape that we're looking at for the calculus graph, all right? So, let's just explain it here. So, this is the graph that I'm looking at for the original function. This is the type of shape we're looking at, all right? So, this is because a is greater than 0, or you're looking at your derivative being a positive graph. And they want to know, why is it at x is equal to minus 2, how can we say that that is, or why is that a local maximum? Okay, so we can see that the graph is turning there at that point, and they want to know, why is it a local maximum? Well, if you look at the graph itself, all right, you can see that if you were to draw a line at this point on the graph and then another one on the other side, okay, those lines would have different gradients because they're doing different things on either side of x is equal to minus 2. To the left of x minus 2, of x equals minus 2, so if x is less than minus 2 and I'm looking to the left of that graph, we have a positive gradient. So for x is less than minus 2, we're looking at a positive gradient. So in other words, the graph is increasing. So the graph is increasing up to the point x is equal to minus 2. Then at the point x is equal to minus 2, the derivative is 0. But then if we look beyond that point, so if we look from x anywhere to the right, so for x greater than minus 2, we have, if I had to draw a line to the graph, it will slope towards the left, so that means it has a negative gradient. And if it has a negative gradient, it means all the function values are decreasing to the right of minus 2. Okay, so if you have increasing values and then decreasing values after that point must be a local maximum. So therefore, because x less than minus 2, we have increasing values, and for x greater than minus 2, we've got decreasing values. This implies, therefore, x equals minus 2 is a local maximum. Okay, so it's a local maximum because we're going from increasing values to decreasing values, so that's got to be a maximum at that point. Okay, I think we're going to quickly do a basic derivative question and then maybe take a quick break before we go to paper 3 work. All right, and it's obviously one that you guys are familiar with. You've seen deriving questions, deriving by rule over and over again. All right, so let's have a quick look at that. We need to find the derivative, dy dx, if y is equal to, and they give you an expression. Now, some of the pointers that you need to remember. In order for you to derive, you need to have single terms. Okay, they need to be separated by pluses and minuses. Your x's should not be in the denominator. If you have x's in the denominator, you need to use your exponent laws and take them to the numerator. You cannot have x in the denominator when you're using your derivative rules. Another thing is you cannot have square roots and all of brackets and that kind of thing. You want things to be as simple as possible. So if you have things like a square root, once again, you need to use exponents to get that out of the square root. So the first thing we need to do here is to rewrite this, and the 2 is fine where it is because it's not an x, okay? There's no deriving that's going to happen to the 2, so that can stay where it is. The first term is fine as it is, x to the power 6 over 2, but we have a problem with this one because it's under a root sign. Now remember, root of x from exponent laws, if I want to take it out of the root sign, it's going to be x to the power whatever's inside the square root divided by that power there. So it's going to be x to the power of 1 over 2. Okay, so this is going to be 4 times x to the power of a half. Okay, and that rule, guys, I cannot stress enough how important exponents are. They come up in logs, they come up in calculus, they come up all over the place. So make sure you understand your exponent rules. But that law, root of x is equal to x to the half. It's coming from your exponent law. I'm just going to make a little side note here. If you've got a to the power of m, and we're taking the nth root, to get that out of the root sign, to write it as a rational power, it's going to be a to the power of m over n. Okay, so that's just a little side note of why we could write root x as x to the power of a half. It comes from exponents. If you've got the nth root of any number to any power, it's always that number from inside the base of the exponent is going to be raised to the power m over n. Okay, all right. So now that we have y in this form with separate terms, we can now use our rules for deriving. Remember, when you derive, you put in a prime sign, okay, to show that you are deriving. If you don't put that in, we don't know that you're deriving because it looks like it's still y. Okay, so you need to put that sign in to show that you've started deriving. From the rules for deriving, we're going to take the power of the x, bring it to the front of this x. So it's going to be 6 times 1, which is 6. And then from the power of x, we subtract 1. All right, and then this side's the same thing. It's going to be 4. Bring the power of the x, times it to the coefficients. And then from your power, okay, and I'm just going to have to get rid of this so I can get a little bit of space here. Whoopsie. Okay, from your power, you subtract 1. It's going to be x to the power a half minus 1. Okay, so simplifying that, 6 divided by 2 is just going to give us 3. X to the power 6 minus 1, which is 5. 4 times a half is just 2. And then x to the power a half minus 1 is just negative a half. Okay, you can leave it there, but sometimes they say write with positive exponents. Then we can rewrite x to the minus a half using, once again, your rules for exponents. We can write this as 2 over x to the positive a half, because remember, if you want to make a power, if you want to change its sign, you need to change its position. So it's in the numerator now. To make that minus a half positive, I need to move it to the denominator. So it becomes 2 over x to the half, which is 2 over root x. All right, so I think this is a good place for us to take a quick break before we get into paper 3.
Okay, awesome. And I know many of you have been asking for paper 3 questions. We promised you that we'd do it, so we will do it after the break. Make sure that you have everything ready. Ask questions, guys, on what is done. Don't bring new questions, because then what happens is that there's confusion. Like, some people are asking about this, some people are asking about that. So make sure that you ask on what Natasha is doing today. Your questions will be answered, but they may be answered in the next revision sessions. So just be patient, because we will get through all your revision, guys. We promise you. See you now.